Okay, today we're building on yesterday's concept. So yesterday we talked about factor trees. The idea of how we should be able to take any number and break it up into prime factors. For example, here's one on the board, 27. Okay. You should be able to recognize that 27 is like, say, 3 and 9 is 3 and 3, and break it up into its prime factors. And factors are smaller parts of the number. Multiples are when that number gets bigger and bigger and bigger. We're going to use that today to help us solve problems involving something called radicals. For the most part, this is going to be somewhat review of grade 10, and then we're going to build into some stuff that's new. But for at least a little while, hopefully this is what you did last year. Regardless of whether you're with me or Miss Ashley, you should have done at least something with radicals. Okay. So why don't I start off with just terminology? You guys good to go here? Okay. A radical is basically a square root. And like a square root uses this symbol here. You guys have seen that before, right? But it could be a cubed root. It could be a fourth root. It could be a fifth root. You guys have heard of the different kinds of roots there are? If it's a square root, we don't put the number 2 in the corner, but it's kind of implied it's a square root. Okay. It seems silly that I should go through this if you already know this, but I want to make sure you guys all know where to find root buttons on your calculator. So you guys know that if you want to like say square root 25, that's where you go for that. Do you guys know where to find the cube root button? Because there is no cube root button on this calculator that's directly visible. Do you guys know where to find it? Press math, then go down to this one here. This will now cube root, and if I say cube root of 27, then that would work. Okay, do you guys know how to type in a fourth or a fifth root then? Has anyone ever shown you this before? The button you want is still under math, but it's number 5, it's X root. Can you guys see that? This little X root right here? Except you don't type this in first. You actually have to say that I want the fourth root, so type in 4, then go math, X root, and then now this will fourth root a number for you. So what's the number that actually fourth roots? 81, I think. Because 81 fourth roots down to 3. You guys all seen where that is before? I just want to make sure you all know how to find different root buttons on your calculator. Okay, now one of the things I want you guys to be able to do is just recognize that sometimes if there's no point in actually finding what the decimal value is. Like for example, does 4 square root? Sure, it's square roots to 2. So in this case right here, why not square root 4 and write it as 2? But does the square root of 3, does it equal the whole number? No, it's like 1.7 something. This is like 1.41 dot dot dot. I think this is 1.7 something. Do you guys know the word irrational numbers? Ever heard that before? Irrational numbers are numbers that like you can't write them as fractions. They don't repeat. They literally go on and on for forever. The most common example of an irrational number is pi. You guys ever heard of pi? Not pumpkin pie, which is delicious. You're gonna be so good on Monday. But like 3.14, 159, etc., etc., etc. Okay, pi is a great example of an irrational number because it keeps going for forever. Same thing with these things here, like root 2. Just keeps going for forever. There's no repeating to it. Okay. One thing that I want to impress on you guys here, do not give me the rounded decimal number. There's almost no use for it. Most of the time, what we'd really like to do is just leave it as root 2. Leave it as root 3. Sorry, give me a second. Hello. She is? Okay. Sure. Maddie. Charlene's looking for you. Okay, so anyways, our goal, as you can see down here, I want to work on learning how to simplify radicals. And that's actually kind of a lot. You guys learned how to simplify radicals in grade 10. We're just going to then build on simplifying radicals a bit after we get there. So let's do some examples here. If I were to give you guys the square root of 25, I'm sure most of you know that the square root of 25 is 5. But I want to talk about why. Okay, sometimes we gloss over this. I want to really go back to the basics. pause for a second. There are lots of different operations in math. Like, for example, adding and subtracting. You know how adding and subtracting are like literally opposites of each other? If you want to undo add, subtract. If you want to undo multiply, divide. If you want to undo an exponent, square root. Does that make sense? So what I'm trying to show you on this slide right here is that really, if you can write 25 as 5 squared, this squared right here is an exponent. That's a mathematical operation, just like adding is. How do you undo a square? Well, you square root. So if you ever have a square and a square root, essentially, they cancel each other. You guys know how, like, in our algebra, you might have, like, 6x equals 5 plus 3x. How do you get rid of this plus 3x? You subtract 3x from both sides. These are opposite operations of each other. Well, that same thing applies here. If you have a cube, how do you undo a cube? Cube root. So if this kind of makes sense here, if you can write 25 as 5 squared, then that's the root of it. I think I got another slide just like this on here. Our goal today is to be able to like reduce these as much as you possibly can. So you know how we broke up in factor trees the other day the number 72? Let's try to break 72 up into certain values. Let's see, there's got to be 8 times 9. 9 could be 3 times 3. 8 could be 4 times 2, and 4 times 2. Oh, no, 2 times 2. That makes sense so far? So in a way, I could really write root 72 as 2 times 2 times 2 times 3 times 3. Now, most of the time, you guys aren't going to solve it like this. Okay, like there's much faster ways of doing this. I'm only going through this because I want to make sure you understand what we're doing and why, and then we'll speed it up later. Is everybody okay in saying 72 is really 2, 2, 2, and 3, 3? Okay. I'm asking you to square root things. What is the opposite of a square root? Something that is squared. Now, currently, all of these numbers in this format are literally written to the power of 1. So why don't I combine any of them that I can and start making things squared? Well, why don't I take these first two 2's here? Let's make it 2 squared. Why wouldn't I add in this extra 2? I don't have 2 of them. I only want things that are in squared format. So this 2 right here, sadly, can't be squared. So I'll just leave it as a 2 to the 1. What about this 3 right here, though? I can write it as 3 squared. Well, here's how this would work then. The square root can undo any of the squareds. So this guy right here was squared. I can undo that square root for this guy here and just have just regular old 2. This 3 squared, the square root can undo that squared and just give me good old 3. But what about this extra 2 that's kicking around here? Can it be square rooted? No. So it has to remain under the square root sign, giving us a final answer of 2 times 3 for 6 root 2. You guys remember doing this last year? Something like this. Maybe different methods, different ways of showing it, but the idea of somehow trying to take this thing right here and turn it into this one right here. In terms of terminology, this is an entire radical, this is a mixed radical. The idea here is that there's now a number in front, a coefficient. Here's another visual example kind of showing what's happening here. Let's say I wanted you to reduce root 50. So again, make a factor tree. So 2 and 25. 25 is 5 times 5. Once you pick up on this, though, you maybe don't even need to do every single step. You would just say, okay, well, 2 times 5 times 5. Hey, these 5s, they're squared. The squared gets undone by the square root, so you just have a normal 5. Let's see how this 2 right here, there's only one of them. Because there's only one, it has to remain under the square root sign. Now, if I really wanted to, I could take and find what 5 root 2 is and get an actual number. But, like, what value does this have? For those of you guys who are in my science class, in the sciences especially, we hate rounding. Rounding always leads to errors, which is why we have to do sig digs. Like, if we don't have to round, don't round. To me, there is no value in you telling me this is 7.07. Because, first of all, it's not. It's not 7.07. It's 7.071067, know what I'm saying there? And that extra couple of decimal places, telling you in math and science fields, that actually makes a difference. Right? So please, 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 don't do that unless there's some really good reason to. Honestly, just leave it here. Isn't it less work anyways? I want to show you a correlation you guys have been working on recently, the quadratic formula. You guys know how when you did the quadratic formula, you'd get like 3 plus or minus root 7 over 2? And like, honestly, leave that as your final answer. Okay? Don't give me decimal numbers. There's no value in it. Just leave it literally as what you see right here. Cool. Triangle showed up. Just leave it as this. Okay. Let's talk a little bit more about square roots for a bit here. It's actually not possible for you to square root a negative number. You guys have probably heard that at some point in your life. But I want to talk about why it's not possible to square root a negative number. Okay? Think about this for a second here. In order to use a square root sign, you need a number that can be squared, right? Like, let me just write something out again here. If I want to square root 9, what I'm really asking you to do is find out that 9 is really 3 squared, and then the square root sign and the squared sign are really canceling. Right? That's really what we're asking you to do. You just have probably skipped over that step in your minds, right? Well, how can I write negative 5 as a number that's squared? You know what I'm saying? Like, how can I take this negative 5 and write it as a number that's squared? When you square a number, it always has to be positive, right? Like any number that goes inside here, when I square it, it actually is a positive number, right? So if this number here were like, say, 2 squared, well, 2 squared would give you 4, which would be positive. How do I get a negative number there? Let's say this was a negative number. Say that somehow was a negative number there. A negative times a negative squared would actually give you a positive right here. So it's physically impossible to find two numbers that, like, when you multiply them by each other and you square them, that somehow it ends up being a negative. It's physically impossible. Right? Positive times positive gives you positive. Negative times negative gives you positive. But you can't use a positive and a negative to get to the negative, because literally it has to be the same thing twice, right? So hopefully that helps explain why square roots can never be negative. Okay, another thing I want to talk about here. If radicals have the same radicand, I don't know that I've used that word yet today. Do you guys know what a radicand is? It's like the stuff under the square root sign. They're called like radicals. Like, for example, this one right here and this one right here, they're considered like radicals. The radicand in both cases is root 5. See, there's a 4 in front of this number right here. What's the number in front of this one here? 1. Really, right here I'm telling you that you have 1 root 5. And right here you have 4 root 5s. In a way, this is no different than algebra. If I were to ask you to take 1 root 5 and add it to 4 more root 5s, this is now going to be 5 root 5s. How different is this than saying you have 1 something, 1x, add it to 4 more of that same something. When you're done, you have 5 of that something. You see how those are like terms? Do not do this, because that's not how they work. You don't take 1 and 4 and add it up to 5, and then take 5 and 5 and add it up to give 10. That's not how you solve these. Does that make sense? Like, literally, you have 1 of something, you have 4 of that same something, so when you're done, you have 5 of that same something. Okay, so the term I want you guys to know is that if they have the same square root, exactly the same square root, you can put them together. They're considered like terms. If not, they're not. What else should we talk about here? Exponent rules. Okay. Sometimes we write square roots in a different notation. This really took off, in my opinion, more during the computer age. Okay. When you're writing code or script of some kind, and you want to show that you want a square root, some computers, they have this button right here. They have a square root they can do. But another way of writing it text-wise would be to say this: n to the power of 1 over 2. This would be a good computer script way of writing a square root. If you ever see a 1/2 as an exponent, it's a square root. If you ever see a 1/3 as an exponent, it's a cubed root. A 1/4, fourth root. Okay, so this is like a good way of like writing it in another format. This really means the square root of n. Imagine that you were trying to text your friend help for math. Anyone ever tried to do that before? Sometimes I try to email people to help them for math, and math is super hard to do over typing, right? Because on the keyboard there is not a square root button on a keyboard, right? But what I can do is I can type something. This little thing right here means exponent 1/2. If it's n to the power of a half, it makes the square root. You guys ever seen that before? So I just want you to be aware that's another way we could write things. Okay, so let's try a couple of examples now that I've talked through some basics. Let's simplify these. Now, after a while, some people start actually speeding things up a little bit. They might say, well, rather than breaking down the tree all the way there, why don't I make this like, say, 40 times 2, 20 times another 2, 5 times 4. Maybe they would even stop there. Can one of you guys grab the door? Grab the door. Thanks. Maybe for the first one even, I'll keep breaking this up. I'll break it up into a couple more 2s. What I think I showed my class last year, you guys will have to remind me what I showed you, is once you've broken this down, I would circle them in groups of 2, and I'd say, okay, well, look, I have 2 2s. Is that what you did? Perfect, okay. You have 2 more 2s. So this becomes like a real number 2. This becomes a real number 2. But this 5 right here is stuck. So my final answer is going to be the root 5 is left over. This becomes a real 2. This becomes a real 2. And when we multiply 2 by 2, we get 4. Any of you guys able to do that kind of without my help? Remember doing this? Okay, cool. Let's speed it up now then. Once we get the idea, rather than making a full-on factor tree, let's just start looking for numbers that we know actually square root. Okay? What numbers actually square root? 4, 9, 16, 25, 36. Those kind of numbers, right? When we break these guys up into the 2 choices of numbers here, why don't we just break it up into numbers that we know are going to square root anyways? For example, 63, let's break it up into 9 and 7. It's actually probably the only combo that works. But 9 square roots to give you 3, right? So if 9 can square root to give you 3, can 7 square root? No. So just leave that one behind. Can I redo the first one then a little bit faster? Here's what I might do for the 80. I might take 80 and I'm going to look for perfect square numbers that go into 80. So I'm going to try this. I'm going to take 80 and I'm going to divide it by 4. Okay, it divides by 4. I'm going to keep going though. What if I took 80 and tried to divide it by the next perfect square,
Mr. Cleaver, can you please come
which
to the
is
office?
9?
Mr. Cleaver, please come to the office.
Okay, 80 doesn't divide by 9. What if I try the next perfect square? 80 divided by 16. You guys know where I'm getting the 4, 9, and 16 from, right? 2 squared, 3 squared, and 4 squared. Check this out. Hey, 16 actually goes into 80. Well, rather than breaking it up, you know how I broke it up into 4 and 20 the first time around? What if I just went right to 16 and 5? And then I'd say, hang on, doesn't 16 actually square root to give me 4? And doesn't 5 just have to stay as a 5? Isn't that maybe a little bit faster? So all you need to do is look for very targeted numbers. Only the ones that actually are square numbers work. So 1, 4, 9, 16, 25, 36, 49, right? Only bother with those ones. If those ones don't work, then we're done. But what if it's a cube root? Well, then we need to look for numbers that are perfect cubes. Anybody know what the cubed numbers are off the top of your heads? What's the first one after 1? 2 cubed is? Okay, so why don't we try that? Can 144 divide by 8? Hey, perfect, it does. Let's go bigger, though. What if there's a bigger number than that works? So 2 times 2 times 2 was 8. 3 times 3 times 3 was 27. Can 144 divide by 27? No. What about 4 times 4 times 4? Is that 64? Okay, that doesn't work. What about 5 times 5 times 5? That's 125. I think we're getting to the point where I may as well quit. So what is the biggest What's the biggest perfect cube that seems to evenly divide? I think it was the 8, right? So when I write this out now, I'm very purposefully going to break it up into 8, and I shouldn't put the calculator away. What was it? 8 and... Thank you. Okay. I mean, I could, in theory, have broken this up into 12 and 12, right? Like, isn't 144 12 and 12? Why should I not pick 12 and 12? Neither of those numbers can cube root. Does that make sense? Only pick a number if one of them cube roots. So, does 8 cube root? Yeah. 8 cube roots to 2. Does 18 cube root, though? Okay, so just leave it as the cube root of 18 then. So rather than doing a full-on factor tree, be a little more targeted in your approach and only factor out numbers that are either perfect squares or perfect cubes. If not, don't bother. So let's try a couple more here. Because some of these I'm doing on purpose here to make a point. 26. There are clearly numbers that multiply to give 26. But the only ones I can think of are 1 and 26 and 2 and 13. Are any of those numbers that I just said a perfect square number? Right? I mean, even though in theory I could break this up into 2 and 13 or into 1 and 26. Come on back. There you go. Since none of them are actually square rootable numbers, I guess I'm done. This one literally has to stay as root 26. We're done. What about the cube root of 40? So think about cubed numbers now. We're talking about 8. Does 40 divide by 8? Yeah, it does actually. 40 gives you 8 and 5. Can 8 square root? No. But we don't want square roots this time. We want cubed roots. Can 8 cube root? Yeah. 8 cube roots to give you 2. Can 5 cube root? No, so just leave it as the cube root of 5. Now we have our simplified value. Makes sense. I want to use that to illustrate this last one, because this one I have on purpose here, 400. 400 literally breaks up into like 20 different combos, I'm sure. 1 and 400, 2 and 200, 4 and 100. I bet you it divides by 5, I bet you it divides by 8, I bet you it divides by 10 and 12, and you know what I mean? Like, there's a million ways you can break this guy up. So why don't we only break it up into a number that's actually square rootable? Like, say, 100, because 100 goes into there, and 4. Now, this one I want to point out, though. What happens if both numbers are square rootable? Because 100 square roots to give you 10, right? 4 square roots to give you 2. What's my final answer, then? What about under the root sign? Yeah. In theory, you could write it as 20 root 1. We would never do that, though, because what's the square root of 1? 1. So, like, this is kind of dumb to do, but in theory, I could always times this by 1. Right? This could be 400 times by 1, which means there's a root 1 left over, which means there's a root 1 left over. So I just want to point out that sometimes both parts actually work, and you don't even need to have the square root sign. So don't forget to consider that as well, because that's always a possibility. How am I doing so far? Is this familiar? Okay, I'm going to fast forward to something that's maybe newer. Shoot, I should do this, though. I shouldn't skip here. We can also go backwards. Going backwards means that you take this coefficient and you put it back under the square root sign. Only just put it back under the square root sign as a squared number. Like, here's how you do this one. You'd still have your 5 there. How did this 2 get out in the first place? Well, because there was 2 of them, which was really a 4, right? This 4 square rooted to give you 2. Right? So I'm just going to put the 2 back underneath the square root sign, but it doesn't go back under as 2, it goes back as 4. So this was root 20. Or this one right here. This cubed root of 3 is still going to be there. This 2, it got to come out of the square root sign, though, because it was actually the number 8. Because 8 cubed rooted pulled out to give you 2. So then this would be going the other way. Okay. Here's what I want to focus on now. This is what we may have done a little less of last year. I know kids in my side of 10-C, I tried to put some letters in there just because I knew this was coming later. But this wasn't our main focus last year. The question now is, what happens if we have variables? Can we still do this? So first thing we want to talk about is what happens if I give you 8 over 3? What kind of root is that? It's a cubed root. I want to go back a few slides. Remember how I showed you that if you ever have a fraction tells you what kind of root you have? If you ever see something like this, 8 over 3, this 3 right here really means that you actually have a cubed root. So another way of writing this is that you have the cubed root of x to the 8. Keep the 8, but the over 3 tells you what kind of root you have. Now, this still works the same way as before, only we have to approach it just a little differently. What does x to the 8 really mean? Well, it means x times 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 x. I'm going to go through the motions of writing it out. Literally, x to the 8 means you've got 1, 2, 3, 4, 5, 6, 7, 8 x's. Okay, let me go back a little bit here. Remember when we were doing this with numbers? If you had a group of 2 or a group of 3 numbers, you could actually root them, right? By virtue of this being a cubed root, we need them in groups of 3, because it's a cubed root. So in a way, these 3 guys right here are an x cubed. These 3 guys right here are an x cubed. These 2 guys right here, though, we don't have enough for a group of 3, right? So all that's left is an x squared. What happens when you cube root x to the 3? What happens when you cube root x to the 3? I'm asking you to cube root x to the 3. Aren't those literally the exact opposites of each other? Just like add and subtract, multiply and divide. One day you guys will do exponents and logarithms like they're doing over there. Right? These 2 functions, really, they're the opposites of each other. So this thing right here just becomes a single x. Well, this next group of 3, the exact same thing. We have another x. So this thing right here can totally cube root. These 3 right here can totally cube root. What about the 2, though? I don't have enough, right? I needed a group of 3 for them to cube root, so I'm going to have to leave x squared under the cube root sign. Makes sense? This group of 3 comes outside the sign and became this one here. This group of 3 also comes outside the sign and goes right here. But this group of 2 I didn't have enough of, so that's why they're stuck behind. One last thing, I probably wouldn't write it like this though. X times x, x squared or 2x? Should it be x squared or should it be 2x? X squared. Don't forget we're multiplying these by each other. This is x times x. If it was x plus x, it would be 2x. But it's not, it's times. So probably the best way of writing this now would be x squared is now outside the square root, the cube root side. But there are also some that remained. Should this number right here ever be bigger than this number here? It's got to be smaller, right? Because if you had 3 of these or 4 of these or 5 of these, you could pull some more out front. So when you're done, whatever the type of root that you have is, this exponent that's left over better be smaller. It just means those are like the leftovers. So let me try one more example with you guys. Let's try it with numbers and letters now. This is really the new change. In 10C, you definitely should have worked with numbers. They use square root. In 20-1 or 20-2, really doesn't matter which one you're in. Both curriculums require us now to work with variables as well, which you might have done last year. I know I did it with the kids that I taught. So let's break this up here. How do we break up the number 63? What does it break into? What was that? Perfect, 9 and 7. Which of those numbers is useful to us? The 9 or the 7? The 9, because 9 square roots to give you 3. So why don't I put a 3 on the outside, and I'll start a square root, and I'll leave the 7 inside. So the 3 was able to escape, the 7 is stuck. Okay, you got 5 x's. If you really need to, write them out. 1, 2, 3, 4, 5. What kind of groupings do we need now? Cube root, square root. We need square root, right? So we need them in groups of 2. So here's one group of 2. That puts an x on the outside. Here's another group of 2. That puts a second x on the outside. Here is a group of 1. Sorry, not enough. You got to stay behind. But you also have y squared. I mean, I've been talking about this all class. What happens when you square root something squared? Well, the square root and the squared just are gone, right? So the only thing you're left with is y. Or you could approach it like this. Y squared really means you have two of them. You could even say this times 1 if you really wanted. The group of 2 can now come outside, and what's left over? I guess there's a 1 stuck behind, but we would never write that 1. Right? So there's your final answer. Anybody remember doing this at all, or something similar to this? Yeah. Okay. And if not, that's fine. I was trying to extend last year for some kids. But that's our goal, is we need to be able to work now with not just numbers, but also with letters. And that throws kids off sometimes because it's a little more challenging. Let me skip ahead here because I want to get done earlier. Can I go to this slide right here? Can you guys find the simplest form slide? Ultimately, here's my goal for the day. I need you guys to be able to simplify radicals that either involve numbers or letters. Okay? And when you simplify, there's 2 requirements for everything to be considered simplified. And one of these we've been working with already. The second one I'm going to have to pause and come back to next week when we do more notes. So we'll just say the second bullet, but I'm going to skip it till later. Here's what makes something be in simplest form. The radicand is like what's under the square root sign, right? Does not contain any factors that could be removed. If there's still something underneath here that you can pull out front, you should do that. Okay? That's what makes it considered simplified. There's one more thing that makes it simplified. You actually cannot have a radical in the denominator of a fraction, which we haven't covered yet, but basically the rule would be that this right here is not considered simplified. Because can you guys see how there's a square root on the bottom? Okay. Now, this has not come up for you guys yet, so don't worry about the second bullet. I'm going to talk about it another day, but at least for right now, if the square root has something that can get pulled out, you need to do that. Ella. Yeah. Yeah. No, it was in like one of the common areas. Yeah, Kevin said there was some leftover ones. It was in the senior high, like fishbowl area. Okay. Totally. Okay. Okay. Cool. Okay. Okay. Thank you. Sorry. Okay. Simplest form. I want to show a slide here on the quadratic formula. You guys have actually been doing this already in our first unit, right? When you use the quadratic formula, quadratics involve having to square root numbers. And hopefully one of the things you picked up on is that whatever you get under the square root sign, you may have to do something with that. Like see in this one here, see how there's root 25? Well, if you can actually square root it, you should turn 25 into 5. But I think I had a second one of these here. What if this thing right here was 720? Did any of you guys get tripped up on one of the quizzes where you didn't simplify this number right here? Because I know it was on one of the quizzes where this value right here could be simplified. You know, maybe you'll know the one I'm talking about here. If this right here was a 720, you should not leave it like this. This is not done yet when you work with quadratics. The reason why is that 720 totally has numbers that you can kind of like pull out front. And if you can follow this person's work, they took 720 and made it 144 times 5. Why did they choose 144 and 5? Like, why? What was their rationale? Well, one of those numbers is really helpful, right? The 144, right? Because 144 right here actually square roots to give you 12. The 5 sticks behind it. And then, depends on how you cancel, but essentially this 24, this 12, and this 8, they can all be reduced, and you can lower them back down. Like, they can all be divided by 4. So if you divide 24 by 4, you get 6. Divide 12 by 4, you get 3. Divide 8 by 4, you get 2. This would be the proper way of reducing something. Because what's ended up happening now is rather than this being a larger fraction, it's now been reduced. So from this point on, definitely, I would expect that anytime you have a square root value, if it was like, say, 6, fine, you're done. But if it's root 20, 20 is not done. Because what can 20 multiply to give? 4 and 5. Which one of those is useful? 4, because it square roots. Okay, last thoughts, then we'll take off here. Let's do one more example of the quadratic formula now. Let's say you got to this. This is not good enough. We want to try to break this up even further. So here's what I recommend. Let's deal with the 160 right here. What sort of roots can you pull out of 160? I mean, definitely 4, right? 160 does divide by 4. But I feel like I can do better than 4. So 160 will divide by 16. What else? 25? Nope. 36? Nope. You guys get where I'm getting the 16 and the 25 and the 36 from? What would the next one be that I should try if I'm even going to try now? 49. I'm not even going to try 49. I'm pretty sure we're done, right? So the biggest square rootable number I could find, I think, was 16. So now I might say, well, this is 16 by 10. 10 doesn't square root, but 16 does, right? So here's how I'd write it. Minus 4, plus or minus, and then this guy right here, since 16 square roots to 4, we get 4 root 10. Last step. This 4, and this 8 can all be reduced. 4, 4, and 8. We already did multiples, right? 4, 4, and 8 are all multiples of the number 4. So divide them all by 4. Divide this by 4, make it a 1. Divide this by 4, make it a 1. Divide this by 4, make it a 2. Here's the best answer. Negative 1 plus or minus 1 root 10 over 2. This would be considered the best answer for how you use the quadratic formula. Well, actually, no. What wouldn't I actually include in that, probably? Yeah, like we wouldn't write this 1 right here, probably. Does that make sense? Okay. I think I have like just a few last slides, right? We're almost done these? Yes. Okay. So what I want to do now is I want to give you guys a little tease as to what we're doing next week. Okay? Next week what we're going to do is we're going to talk about how to do operations on numbers. So I need you guys to be able to do things like multiply and divide and add and subtract things that have square roots. And you've already somewhat probably done this in grade 9 and grade 10. So I want to just do a few examples. And then if you've already seen this before, hopefully that makes sense. If not, literally that's our next topic. Like topic 3 is all about how to combine radicals. But just as like a little tease, just to see whether or not you've done this before, I want to try a couple. Like say this one here. What if I asked you to take root 2 and times by root 6? Does anybody know what the answer is going to be? Well, literally, you take root and times by root, and it gives you a root 12. Because this 2 and this 6 can multiply to give you 12. Except, hang on a second. 12 can be rebroken back down, though. Now, 12 is 2 times 6, but it's also 3 times 4. Why do I want the 4? Because it square roots to give us 2. So the best answer is this, 2 root 3. We could divide. Well, same thing with dividing. 18 divides by 2 to give you, well, 9. But 9 square roots, literally to give you 3. Here's an example of multiply. Here's an example of divide. Literally, all you do is you take the coefficients inside like this, and you multiply or divide them by each other. The other thing we're going to work on is, well, what happens if I give you mixed radicals? And maybe you've seen this, maybe you haven't. But here's how you'd solve this one. You take the 3 and the 2, you take your coefficients, you multiply your coefficients by each other. So 3 times 2 gives you 6. Then you take your rooted numbers, and you times those by each other. Then we're going to calculate what's 7 times 14. 98. Brief aside, this is kind of like taking 3x and timesing by 4x squared. How do you multiply these together? Well, you take the coefficients and you multiply them to give you 12. And then you take the other part and you put them together to give you x to the 3. That makes sense? So you always take coefficient by coefficient, radicand by radicand. Is that done, though? Actually, no. 98 doesn't divide by 4, doesn't divide by 9, doesn't divide by 16 or 25 or 36, but actually divides by 49. Yeah. So if this guy breaks up into 49 and 2, then the 49 square roots to give you 7. So you then have 6 times 7, root 2. So this would be your final answer. Can I blitz through that? I'm going to actually show you this more next week, but did anybody ever seen that before? Okay. If not, don't stress it. Do you want me to explain that one more time? For sure. 98 is 49 by 2. When you square root 49, it gives you 7. When you square root 2, you're stuck. So the 2 stays here, and the 7 goes there. Okay, let me do one more, and then we'll call it a day. What if I give you this? This is kind of our main goal for next week, Tuesday. What if I give you root 45 minus root 20? The answer, by the way, is not root 25 because of like radicals. Okay? The radicands are not the same here. Right? In order to add or subtract things, let me do another example here. If I give you 2x plus 2y, can you add those together? No, because you have different things, right? If I gave you 1/2 and I gave you 1/3, although you can use common denominators, you're really not talking about the same thing, right? So these guys right here don't have like radicands. But what if I simplify first? What numbers multiply to give 45? Okay, 5 and 9. We want the 9 because it's square roots to give me a 3. What multiplies to give 20? We want the 4 because it's square roots to give me a 2. Hey, hang on a sec here. We now have 3 somethings. We are minusing 2 somethings. 3 minus 2 gives me 1 something. It's no different than 3x minus 2x. But here's the kicker, though. These guys right here have to have the same radicand. If they don't, it's no good. Okay, so that really wasn't the point of my lesson today so much because we're going to focus on that on Wednesday. But if you've seen that before, that's kind of where we're going. If not, then we'll build towards it. So, quick summary. The one thing I need you guys to be able to do, the 2 things I need to be able to do. Can you take a square root and pull numbers outside of it? Can you also take a square root and pull letters outside of it as well? If we have x's and y's and 64s, can you do that as well? Okay. One last thought. I know I'm stealing your guys' skills journals for the weekend. Does anyone have one of those books nearby, though? You have one here. There are a ton of practice questions you can work on starting Tuesday on how to simplify exponents. Like there's a whole page in the first section here on fractions, radicals, and exponents that you guys can start working on. So starting next week, Tuesday, when we give you your books back, then you guys can work on that sort of stuff. Sound good? Okay, last thought here. If I have your signed form, you guys can take off early for the holidays. If I don't have your signed form, why do I not have your signed form? It's a month into the year. So you have to stick around. Otherwise, you guys can take off. By the way, yeah, I'll take progress logs anytime you got them.
How many times do
But
have to unit it?
you... Oh, hang on a second. Let me stop this first.